we have part A, which says 30 kVA, 2400 stroke 120 volts, 50 Hz single phase transformer, has a high voltage winding resistance of 0.1 resistance, 0.1 ohm, and a leakage reactance of 0.22 ohms. The low voltage winding resistance. Okay, so when you look at this, it is high voltage stroke low voltage. So this is primary, this is secondary. Now what does that mean? If they are telling us that the high voltage winding resistance is 0.1 ohm, they are telling us that resistance R1 is 0.1 ohm and reactance X1 is equal to 0.22 ohms. So this is referred, okay, not yet referred, but basically we are talking about it in reference to the second, in reference to the primary. So what is R2? R2, that is the one of low voltage. So we have 0.35 ohms, and X2 is 0.012 ohms. So find the equivalent winding resistance and reactance when referred to the low voltage side. So when referred to the low voltage side, they are telling us resistance, we can take it to be RO2, and reactance XO2, that is referred to secondary side. So that's what they are telling us. Now what we do, we already know that that RO2 will always equal to R2 plus R1 times the transformation ratio. But what is K, which is the transformation ratio, is 120 divided by 2400. Is always the voltage on the secondary, the voltage rating of the secondary winding divided by the voltage rating of the primary winding. So this is going to give us, this gives us 0.05. So that means RO2 will equal to R2, whereas R2 is 0.035 plus R1, which is 0.1 times 0.05 squared. So if I evaluate that, I get 0.03525 ohms. And that's done. Then XO2 will also equal to X2 plus X1 K squared. And this is going to be what is XO2. XO2. So we have X2, which is 0.012. So we have 0.012 plus 0.05 squared times X1, and X1 is 0.22. So I have 0.05 squared times 0.22 plus 0.012, and this gives us 0.01255 ohms. So the equivalent resistance and reactance when referred to the low voltage side or the secondary voltage side are as calculated. So let's go to part B. Part B says 3300 stroke 230 volts, 50 Hz one phase transformer is to be worked at a maximum flux density of 1.2 webers per square meter in the core. The effective cross-sectional area of the transformer is 150 square centimeters. Calculate the suitable values of primary and secondary turns. So part B is 3300 stroke is 330 stroke to 30 volts, and we are told that area is equal to 150 square centimeters. This is equal to 150 times 10 power negative 4 meters squared. And we are told that the maximum flux density is 1.2 Webers per square meter. So according to the transformer equation, the rated RMS for the primary side is always equal to 4.44 times N1, which is the number of turns, times the frequency, times the maximum flux density, times area. So if we are looking for the number of turns, we make N1 the subject of this. So E1 is 3300. Now divide by 4.44 times frequency, which is 50 Hz, times 1.2 times 150 times 10 power negative 4. So if I evaluate that, I'm going to get, so I get 825.8 tons. Therefore, the primary number of tons will be 8, 20, 26. Yes, you can approximate to 826. Then secondary, so N2 will also equal to 230 divided by 4.44 times 50 times 1.2 times 150 times 10 power negative 4. And this is going to be 230 divided by, so finally we have 57.557, so we can approximate this to 58 tons, and that's all. So the secondary number of tons would be 58 tons. Part C. So let's look at part C. That in a 25 kilovolt ampere 2000/200 single phase transformer, the iron and full load copper losses are 350 and 400 watts respectively. Calculate the efficiency at unity power factor on full load and on half load. So it is a 25 kVA 2000/200 volts transformer. The iron losses are equal to 350 watts. The copper losses are equal to 400 watts. So full load copper 400, iron losses 350. So at full load and unity power factor, so power factor equal to 1. So meaning at full load, X is equal to 1. X is the percentage or fraction of the load. Okay, so if it is that, what we do, we are going to look for efficiency, which is equal to kVA rating times the power factor times the amount of load divided by the kVA rating times the power factor times the load plus the losses, which is the copper loss, the iron loss and copper losses. Then we multiply by 100. So efficiency therefore will be 25 times 10 power 3 times the power factor, which is 1 because it is at unity power factor, times the load fraction, which is 1, divided by 25 times 10 power 3 times 1 times 1, then plus the copper losses, which are 400, plus the iron losses, which are 350 times 100. So this is going to be 25 exponent 3 divided by, So what we get here is 0.97087 times 100. This gives us 97.09%. So that is the efficiency of this system at unity power factor and full load. So let's look at case 2 or part 2, half load. So when it is half load, then X is equal to 0.5. So therefore, the percentage efficiency would be the kVA rating times the power factor times X divided by kVA rating times power factor times X plus the iron losses, okay, plus X squared copper losses. Actually, even up here, we should have put X squared times the power, the copper losses. So times 100. So we will have 2 times 10 power 3 times 1 times 0.5. 1 is the power factor and 0.5 is the amount of the load. So 25 times 10 power 3 times 1 times 0.5 plus the copper loss, okay, the iron loss is 350 plus the 0.5 squared times 400 times 100. So when I evaluate this, efficiency will be, so efficiency becomes 0.9653 times 100%. This gives us 96.53%. So ladies and gentlemen, this is how we can attempt such numbers.